Hello, everyone. I will talk about our final project about deep video understanding entities relationship discriminator. So we designed a system that could classify the relationship between two entities, given a set of video clips that contains a visual evidence to prove this relationship that captured from a video. For example, one of the video clips could show entity A hugging and greeting with entity B. The system should give its classification result that the relationship between entity A and entity B is very likely to be friend, given a set of this kind of visual evidence. Generally, we are simulating how humans recognize relationship between people. Humans use previous experience and interactions between people they observe to tell the possible relationship between these two people. We train the model with a set of interactions between two people in a movie as features and their relationship as labels. So why we are interested in this topic? Deep video understanding is a difficult task which requires computer vision system to develop a deep analysis and understanding of the relationship between two different entities in a video. It also requires us to use known information to deduce hidden information and to popularize a knowledge graph with all acquired information. The aim of this proposed task is to push the limits of multimedia analysis techniques to address analyzing long duration videos and extract useful knowledge to utilize them in solving different kinds of queries. This is the graph of our system architecture. The user will send video, entity images, and entity name pair to the system. The input data will be processed by face recognition module first. Key video clips that are highly possible to contain interactions between two entities will be captured from video. Then they will be sent to grounded video description module. The grounded video description module will extract features from those clips and generate description from them. Those descriptions will be sent to relationship discriminator module later. A classification mode will be responsible for classifying the most likely relationship from a given relationship set using all those descriptions as evidence.
So here comes the dataset we use in our project. On the right side is the HLVU 2020 dataset. It contains 10 different whole movies. So based on this dataset, the TrackVid 2022 divides these movies into several movie shots with their scene numbers. Also, TrackVid 2022 provides relationships description between different entities in the movies. Next slide, please. And here is the face recognition part of our project. This part is based on the inside face ontology, which is a Python library for 2D and 3D face analysis. We use its functions for face recognition, face detection, and face alignment. For the implementation of inside face, all face images are aligned by MTCNN and cropped to 112 multiple 112. The input face images should be generally center cropped. We use RNet plus ONet of MTCNN to further align the image before sending it to the feature embedding network. Also, the ARSNet network used in our implementation was trained with AR safe face, which we mentioned it in our milestone 2 report. And there's a very important concept used in the inside face ontology, which are the landmarks. Landmarks play a very important role in the face detection part. We can see in the example here, different faces can be detected with these 5 features. And this scene here is about whole family talking in the car. In the first frame here, we can see that in the back seats, the faces of these two people are not captured. But in the following conversation, these characters have a chance to get close-up shots when they are talking or having interactions with others, which is the key clips we want to collect. So actually, we can use it to create some new thoughts here. Next slide, please. And our original thought was to, like for frames containing two or more entities, we can form a 1 minute video clip centered by that frame as one of visual evidence of the relationships between any entities present in that frame. So now we don't need to do that because of the close-up shot that was commonly used in the movies. So for now, we only need to capture the face with the biggest bounding box in each frame, and we can form a 500 frames video clip if there's a change in the detected face. For example, the face A was detected in this frame, but if it is changed to face B detected in the next frame, so now we can know that there might be a interaction happening. So we can collect the video clip. And here are 4 examples during collecting the clips. The first example here is there's no, and this diagram here is the output of the face recognition with each frame. And in the first example here, we can see that there is no face change. So we can conclude that probably no interaction with other people. So in this case, we don't need to collect the video clip. But in the second example here, there are some obvious face changes. So which means interaction probably start. So in this case, we need to collect a 500 frames clip. And here are the third and fourth examples. In the third example here, we can observe that there are some new face changes. So we can conclude that probably another interaction starts. So we need to also collect a 500 frames clip. And in the fourth example here, after the 500 frames clip was collected in the third example, similar phase changes occurs. So in this case, this probably means that new interaction starts. So we need to collect a 500 frames clip again.
So after we obtain a set of video clips that highly possible to contain entity interactions, we will send those clips to 2 different feature extraction functions, Detectron2 and ANET 2016. Detectron is used to detect objects in each frame of each clip. It will return predict objects and their corresponding bounding box in the frame. All those information will be packed up and stored as H5 files, then feed to attention model as regional attention feature later. ANET 2016 feature extractor will extract RGB features for each frame in the clip and pair them with frame numbers to form frame-wise temporal features, which will be packed up and stored as H5 files as well, and sent to attention module as temporal attention features later. During the description generation process, we use pre-trained models and features extracted from previous 2 functions. Features will be processed by attention module and grounding module to generate words. Language generation module will then compose sentences using those words. The relationship discrimination module is a classifier that takes a set of descriptions of interactions between two entities that generated by ground video description module. To normalize the input descriptions, we will factorize them. Then we use KNN model to predict the most likely relationship between two entities as output. For our project, we only use interactions between people as evidence to classify their relationship. Therefore, it is hard to tell the difference between similar relationships that's supported by similar visual interaction evidence. Take an example. It is hard to tell if the relationship between two people is girlfriend and boyfriend or wife and husband. It is hard for human as well if you only watch their interactions. One of the solutions is adding scene detection to compose scenes. Those two people present together as an extra visual evidence to support their relationship. Using same example here, if two people present together in a scene of living room or bathroom, they are more likely to be wife and husband than girlfriends and boyfriend. Also, we detect a lot of unknown faces during our face recognition part. So we try to improve the accuracy of face detection by either improve the algorithm or change another algorithm. And thank you for your watching. This is our final presentation.